Hi there, this is part 2 of a series on how to build a digital stomp box. And today's presentation, I'd like to go through the components used in the stomp box. It's a digital stomp box, and this is what it looks like over here. And we're going to go through some of the interfaces, how it's connected, and go through a couple of very simple software algorithms for the effects. So we're going to do that today. I'm going to go through this little presentation, and so you could get an idea if you ever had to build one of these. This would give you a head start. Okay, so part 2, interfacing modules and more discussion in making a digital guitar stomp box. Okay, so in this project, a STM microelectronics Nucleo 723ZG board is used with a Texas Instruments audio codec TLV 320 AIC 324 to provide a DSP stereo audio processing system. So over here, I just wanted to show you, this is a photograph, a picture of the Nucleo board that I use. So this is all off-the-shelf components that you could buy. I bought this one directly from ST Microelectronics. You could also buy, I believe, from DigiKey. And these cost on the order maybe a little bit less than $30. And the nice thing, they're off the shelf. You don't have to do any surface mount soldering on this, which makes it a lot easier for us hobbyists that don't have the capability to do that. It is a little bit bigger and bulkier than what you need, because you really just need this chip over here. This is the main processor, but it has like a lot of extra stuff on it that helps you to debug it and interface to it. And there's a few switches here. One is a reset switch. Another one I use here is for to capture some data for instrumentation. So we're going to go through this presentation a little bit. So this is used to develop a digital guitar effect stomp box. The software was developed with the free STM Microelectronics STM32Cube IDE application software and was written in C. Now that's really great. All this, the development software is pretty much free for this now. Just a few years ago, you had to pay a lot of money for this development software, but now STM Microelectronics provides it for free. You could download it from their website, and I like to go through a presentation in the future on how to get this software. So the advantage of a digital stomp box over, say, like an analog one is greater flexibility on the types of effects that can be provided by the same hardware box. So the nice thing about this is that you could get millions of different effects. It's all in your imagination of what you would like to do, just using the same hardware over and over again. So unlike an analog stomp box where you would have to build specialized analog circuitry, this one, it's just software that you change in order to get different sound effects. So the Nucleo 723ZG board has an STM32H723ZGT6U microcontroller in it, and that's this big chip over here. So it has, I believe this is a 144 pin device. So this processor runs at 550 megahertz with its timers running at 275 megahertz. So the timers are built into the microcontroller, and it is a pretty fast processor for this type of embedded systems processor. So this processor supports both 64-bit and 32-bit hardware floating point instructions, which is nice. It has an ARM Cortex M7 processor, which supports the 64-bit floating point and 32-bit floating point. And my examples, I'm only going to use 32-bit floating point. I had to use 64-bit before and hadn't seen too much of a difference. But where the computation is very intensive, maybe the 64-bit would pay off. And it's all done in hardware, not software. So you could get an instruction done, a floating point instruction done with like one cycle. So this processor has the floating point hardware, and it also has DMA streams to avoid having the processor having to wait for data. So which is nice. In the background, you could run these DMA streams, so the data from your interfaces will go directly into memory, so you don't have to wait for to hold the processor's been held up waiting for data coming in. So I'd like to point out this is a technological breakthrough that allows such little hardware to provide a digital audio signal processing system that can be used for a digital guitar stomp box. So the nice thing about this is that the technology is there now to do this relatively cheap as a hobbyist on your own. I'm pretty sure there'll probably be systems out there, maybe off the shelf, similar systems you could buy, but I'm trying to give you the most flexibility. You can reuse this for other things, not just for stomp boxes, for whatever else you'd like to do. So the audio codec is in a QFM32 package and was placed on a custom-made PCB board with op amps and other passive components for signal conditioning. So I wanted to show you this little package here. This is the QFM32 package, and I have it soldered to this adapter. This is a dual inline package. It's a 32-pin dual inline package footprint, where this is the QFM32. So I'd like to make a video on how I soldered this on, because that's a whole thing in itself. I'm not too good at doing surface mount as a hobbyist, but I could do a little bit of it. So this codec, the TLV320 AIC 3254, is very small. It only comes in this QFM32 package. So I was able to successfully solder it on this adapter and get it to work. So this is the printed circuit board that I made that this also goes on top of, and I have schematics of that I'm going to provide, and going to make this all open source, provide all the software and schematics and the know-how of this. So a PCB board was made to make it easier to connect the TLV320 AIC 3254 and its components. So I made this printed circuit board. It's a small one. So KiCad or KeyCAD, not too sure how they pronounce it, I believe it might be KeyCAD, was used to make the PCB board. So this is another free software package you could get that will allow you to make printed circuit boards, and it makes these Gerber plot files, and then you send it out, and then the boards come back, and you have to mount on the components yourself. You have to solder them on yourself. I suppose you can get them made, get it already made, but it's probably pretty expensive. But it costs maybe about say another $30 to get 3 of these boards made. So the TLV320 AIC 3254, maybe that chip costs about $5. So this whole thing, all the parts might be about $40 or so. So to move forward, the I2C address of the TLV320 AIC 3254 is hexadecimal 30. An I2S 64-bit stereo digital interface is used between the STM32H723ZG T6U microcontroller and the TLV320 AIC 3254 audio codec. So there's a couple of interfaces going on here. So the main audio interface that's used, that transfers the stereo data in and out. So there's two 32-bit A to Ds and two 32-bit D to A's, a left and right channel built into the system. So that's an I2C interface. So the STM32H724ZG T6U does support full duplex. So it means it could transmit and receive the 64 bits at the same time. So what's really happening, it's really 128 bits, because you have one input 64 bits and the other one coming back is 64 bits. Now there's also an I2C interface between this and the microcontroller, and that's to provide the commands to this, to control this. So there's two digital interfaces. One's called I2C, which allows you to talk to the registers of this device to set it up. And then there's an I2S interface, and that the I2C really only gets put on maybe one time when the processor first starts up. It initializes this device, and then it goes away. But this I2S interface is going on all the time. So the I2S interface is using DMA. DMA stream to get the data into the microcontroller, or the I2C. So it's only on startup of the device. You don't really have to use a DMA stream for that. So moving forward, the frame rate of the system was set to 20,000 hertz. So that means there's 20,000 frames a second that I could process. So even though, like, I'll talk about this a little bit, or even though the processor runs at 550 megahertz, which is much faster than 20,000 hertz, I could generate 20,000 frames a second, and within what's like if you take the 525 megahertz and divide that by the 20,000, that gives me how many instructions are left over that I can use per frame. So the frame rate was set up to 20,000 hertz. This is sufficient for audio processing for guitar pedal effect. A 40,000 hertz frame rate was initially used, but because of overhead processing, it used up many instructions. So 20,000 hertz frame rate was selected to allow for more instructions per frame. So setting the frame rate is done by using an internal timer in the STM32H723ZG T6U microcontroller and using the interrupt to set the timing. This will allow up to 27,500 instructions per frame using the ARM Cortex M7 processor inside the STM32 723ZG T6U microcontroller. So this is the processor here, which is running at 550 megahertz, and there's an interrupt in here that goes off 20,000 times a second that sends the data back and forth using this I2S interface to this audio codec. Now these audio codecs are very common. Hardware like I guess the cell phone technology probably really pushed this because every cell phone has at least one of these in it to get the audio to work. So there's a couple op amps, two op amp, quad op amps, and some. These are all 100K resistors and some capacitors. A lot of this was taken from the data sheet for this audio codec. So I tried to use the designs that were already suggested by the data sheet, and then some of this is a buffer. Now I also have a reset switch on this that I don't normally press, but it does. It's helpful to have it in troubleshooting. Sometimes you have to reset this. So if you do reset this, so you have to run the processor one time to send the instructions to set up the registers of this audio codec. So this project is hosted on a Windows 10 PC, and it uses Cube IDE version 1.11.2. So this is the main STM Microelectronics product that I'm using, and it uses Cube MX 6.7.0. I'm not using Cube MX a whole lot on this. I just use it to generate the end report, the document, the software, the setup for this. So you don't really need this Cube MX unless you want to get the report to document the software. Now I do believe it runs on Linux also, so that might be another video I would like to make on how to set this up on a Linux computer, since Windows is a little bit pricey. So a 1590D aluminum box is used, and that's 7.4 inches by 4.7 inches by 2.2 inches to fit in all the components. This is one of the largest off-the-shelf aluminum boxes that can be purchased. So I did get the standard size box, which is the 1590D, which is a big one, and it is enough to fit all the components inside, but it's a tight squeeze. So in this demonstration, I had been running it with electronics outside the box. It makes it quite a bit easier to repair if something should go wrong. But anyway, it can fit in the box. Hopefully in the future I might be able to miniaturize things a little bit more to make a little bit more space in there. And that would be helpful. So anyway, LCD 1620 I2C two-line display is used to display the selected effect. So this is a off-the-shelf display. It's an I2C interface that I put on this box just to display the effect number and give it a name. So that's very helpful. So 6 500K linear pots are used to adjust parameters of the effects real time. So I put in 6 pots. I numbered them 1, 2, 3, 4, 5, 6, and they're 500K linear scaled pots that you could turn in real time. It goes into the software to vary parameters of the effects. So these pots interface to the 16-bit A to Ds built into the STM327H23ZG T6U microcontroller. So there's plenty of analog to digital converters built into this microcontroller, and so the pots go into that to do more of like an analog type of adjustment. The 1s up and down switches and 10s up and down switches are 4 discrete inputs. So I have a 1s up and down, and what this does, it kind of beeps up the effect 1 increment at a time or down at a time, and this will beep it up 10 effects. So I could put hundreds of effects in here, but to get to them, this is the switches that I use. So when you push this up or down, it'll increment 10 effects. If you push it up or down, it goes just to the next effect. So there's 4 utility switches called switch 1, switch 2, switch 3, switch 4 are discrete inputs and are used to adjust the effects real time. So there's 4 discrete inputs. You push this up, it goes to switch 1, down to switch 2, up to switch 3, down to switch 4. And in that way I could adjust the effect at the time. It's a discrete input rather than giving it an analog input from one of these 6 pots. There's 4 discrete inputs that I could vary that effect. So the stomp box has 2 inputs, left and right, and 2 outputs, left and right, so it's stereo. The left input is directed through the stomp switch, so this is the stomp switch, to allow true bypass. So the left input, normally I would connect the guitar in through the left input. Now if I push this and the light goes out, that means it's in true bypass and the guitar just goes right to the amp. It passes right through this box. But if I push it, then the light lights up and then it goes through the processing, and the output is the processed output. So the stomp switch has an illuminated LED to indicate when the stomp switch is set to direct the signal through the effects. So next we're going to talk about the interfaces, how this box is, how everything is wired up. So this is the connections. So the first connection is going from the Nucleo board, the Nucleo H723ZG, to the PCB board, the audio codec that's on the PCB board. So there's 7 wires involved. So 2 of them are for the I2C interface, and 1, 2, 3, 4, 5, 6, right, 7, and 5 of them are for the I2S interface. So you can see these wires. I'm going to go down to it and show you the picture a couple pages from here. And so you can see this is the Nucleo board and this is the PCB board. So it's an interface that connects this to that. So the next set of interfaces is to connect the pots to the processor. So it's the Nucleo board to the pots. So the pots are driven by the 3.2 volt power supply, and then so each end of the pot there's a red and black wire that goes to the ends of the pots. One's ground, one's a 3.2 volts, and the middle tap goes in and it connects to the Nucleo board. So basically it would be going back down to that diagram, it would be these pots connecting into this board. So you could see a lot of the wirings, how I have them all kind of separated out. So it would be nice to do this all on one printed circuit board and just put it in the box, but I'm buying just off the shelf components to try to put this together. So the next set is the power supplies. Okay, so I have this is going to, it's showing how the power is connected. So might be better to go to that diagram again. Okay, so this orange USB connector is the power coming in, and I just use a power cube to provide the 5 volts in. So you can see the wires running through here, and it runs to these 3 power supplies. One's a 3.2, one's a 1.6 volt, and this one over here is a plus or minus 15 volt. So this power here is running to these, and then these pretty much direct power to the PCB board. There isn't much. This has its own power supplies in it, so I'm not providing any power to this device, but these power supplies are providing it to this PCB board. So this shows it's a listing that shows how that's wired. So VN is the USB power coming out, and then I have USB coming out. The other thing I have that's important is this over here. It's actually this wire. It's not shown connected right now, but what it is, when this box is running standalone without it being connected to a PC, I connect this USB in. So this power here, this 5 volt power is just running right to this this little USB connector. It just has the 5 volts in the ground. So what I do is when I'm downloading software or debugging, I have this, which goes, this USB connector, micro USB, goes directly to the computer, to the PC, and it still runs well with it connected to the PC. It might be a little bit more noisy because you pick up some noise from the PC, but when I'm running standalone, then I pull this out and I put this one in, so that allows me to run standalone. So the next set of connections is the switch to the LED. So this switch, I believe I had a picture of it up here. Okay, this switch, this is a back view of the switch. So I number it 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is the stomp switch, the back of it. So I call this SW1, SW2, SW3, and so forth. In my numbering system here. And yeah, I skipped over a few things, but I'll get back to it. So this shows the switch. So SW8 would be right here, that pin there. This is connecting the LED up. So I take the USB 5 volt power, and I feed that, and it goes to switch 8. That's over here. That's the 5 volt power, and this is going through the middle part of that switch. So SW5 has a 1000 ohm resistor, and then it connects to this LED. So this LED will light when I push the button. So this is the LED hookup through the stomp switch to make that switch light up. So I accidentally did skip over some areas. Okay, so we have the audio jacks to the PCB. So in this design, there's 4 audio jacks. You can see how it's plugged in. There's like 2 on this side and 2 on this side, and they connect. They have little wires that go to this PCB board, which has the audio interfaces. So that those connections are shown here. So it's going to points on the printed circuit board. So I have this, I called it the J5 connector on the printed circuit board that feeds these inputs, and they go to the codecs. So there's 4 jacks. There's a input left, input right, high and ground, and output left and right, high and ground. But some of the audio, though, goes through this switch because it has the true bypass. So the input, left input high, goes to this 4, and the output high goes to 6 over here. So I could direct it either I could either direct it through the switch, or I could direct it to go out from the effect. So this is the switch to the printed circuit board. So switch 7, this is the for the digital processing, goes to the printed circuit board, and 9 goes to the printed circuit board. And then I have this little jumper. This is the true bypass jumper, so it directs like this input to that output. So then if it was in true bypass, the output would the input would come through pin 4, go 1 to 3, back out to 6. But if it's the other way where the computer's feeding it, it would be coming in the 4 out to 7 and 9 back out to 6. So I also have an I2C interface to the LCD from the processor, which takes 4 wires. So these are the connections between the Nucleo H723ZG board and the LCD 620 board. So there's 4 connections between 4 wires. You can see the wires coming off into the box, and they go back out here. So I can work this LCD. Now, I know this might be boring for some of you, but it's the basics on how this thing is interfaced if you had to build something like this, what you need to have. So trying to see, okay, so the next thing we didn't go through is these switches. Okay, so these switches, there's 8 discrete inputs all together, and they go to pins on the microcontroller. So this is the switches, and there's also a ground associated the center part of the switch. So all together, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 connections, 12 wires going from the switches. The switches take up a lot. So that's these 4 switches here. There's 12 wires. I guess that might be it. Yes, it switches there. That goes back into this card. So I could select the ones up, ones down. 10's up, 10's down, switch 1, switch 2, switch 3, switch 4. So that allows me to select those options. So I believe we got it all. So on my website, I'm going to put a lot of the support files on that you could download that goes with the rest of this. So one of the things that it does, it generates a configuration report on the setup. So I'd like to show you that over here. So this is a report that is provided, and it has all the interfaces. It shows all the electronic interfaces. It shows how the pins are set up and used on this device. And I'm not using a lot of the pins, but you can see this is switch 4 and switch 2, and this is part of the I2S interface. So this is the setup. So this kind of establishes the configuration and how the usage, how everything's used. This is the clock setup, the clock tree. Might be a little bit hard to see here, but we can try to zoom in on it, and you can see these clocks. The timers are 275 megahertz. So you have to be careful how a lot of this is set up, but we'll go through that a little bit later. So this is just to go through the interfaces. So this has a lot of things like the ordering of the different drivers and routines, and not too worried about power consumption in this since it runs off a USB brick. So this is important. It has kind of like how all the interfaces are set up. This is the ADC. And this is the DAC, which we're not really using. It's just kind of reserved. And this is one of the I2C interfaces. And the other I2C interface. One's used for the LCD display, and the other one's used for the audio codec. And this is the I2S display. So we're actually running it at 48 kilohertz is a standard I2S Philips standard. And maybe I'll zoom into that one a little bit, the I2S interface. So we're actually running it much faster, but we're only really reading it at 20,000 hertz. So it could run faster. As long as that's faster than what we use it at, then that's good. So we have some of the clock setups, and timer 3 is the main timer that sets the interrupt. So that's an important one. I'll show you a little bit later how to set that up. And timer 4 is used to set up the A to D conversion. The A to D conversion is done at 50 hertz, so it's done relatively slow. This is just for the pots, so that user interface is done relatively slow. And the reason to do it slow, it messes up some of the DMA streams, so you want to make sure that that doesn't interfere with the I2S DMA stream. So there's a UART on here, and that's just used for instrumentation and test purposes, and I'll go and demonstrate how that's used also. And so it gives you a final like system configuration of all the interfaces you're using, and the DMA, how the DMA streams are set up. So there's a DMA stream. There's only 3 of them here. One for the ADC, one for the receiver for the I2S, and the other one's for the transmitter for the I2S interface. And this is our nested vector interrupt controller setup. So the only thing that we are actually, the only interrupt we have is was for timer 3 is over here. So in that one I set it to priority 9, and that's used to provide the 20,000 hertz frame rate. So that's the only interrupt. We only have one interrupt that we're using for this design. There are other interrupts that you need to make the system work that are kind of invisible to us, that the system automatically sets up. So we don't have to worry too much about all this stuff. The only thing we need to worry about is this timer 3 interrupt. So what else do we have here? We have it shows some of the different drivers and the different training material. It's pretty good. It gives you a whole nice summary of kind of locks in the configuration for you, this report. So anyway, I'll make that available. So this is a summary of some of the interfaces. So timer 3, TIM3, is used to provide the 20,000 hertz frame rate. So I have some there's some LEDs that are on the device. I'll show you where those LEDs are. There's 3 LEDs, and they're you could actually see it on the display over here. It's these 3 LEDs that's built into the Nucleo board. There's a LED 1, 2, and 3 that we could illuminate and use. They're like user LEDs. So we'll get back to the page we're at. So the 3 LEDs, so I tied the green one to our major frame tick. So that'll blink at the 20,000 hertz. It's good to hook that maybe to oscilloscope, sometimes examine the timing relative to other things. And the yellow LED right now, LED 2, spare for now. We're not using it for anything. And I tried to set up the red LED 3 to use for a time frame overrun. So if we go over, if we have too much code and we overrun the 20,000 hertz major frame, that'll illuminate to give us an indicator. Yeah, we did something wrong. That we probably shouldn't do that. So timer 4 is used to provide 50 hertz for the pots. So this is the 16-bit A to Ds that interface to the pots. And we reserve 2 outputs, they're 12-bit DACs, and they're not really used for anything, but in the future we might be able to use that to drive something. So we have a virtual COM port that we could dump data, and if we press the blue button on the board, it'll run this, and then it'll dump on the next reset of the box. It'll dump the data to the screen. So if we had to take some data, plot out data, do some instrumentation, that could be helpful. And that's the Blues users button, which is tied to PC13, is used to collect instrumentation data. So we have our I2C interface for the LCD, and we have our switches. So that shows the interface. So what I did is I took a picture of the back of the board, and to make it easier for me to wire this up, I colored in this picture with the colors of the wires, so I know I have interfaces to these points. I tried to use the connections that are already there on the one side that come with the board. I tried to use these, but there wasn't enough, so I added these headers. I soldered these onto the board because this has all the interfaces. See, this board isn't big enough. These headers here, I guess, were reserved more for like our Arduino, aren't there weren't enough of them. So so the whole thing, it's not populated with all the pins with this device, but these outer ones are. So I got these headers, soldered them in, and I'm actually only wired in. I use wire wrap wire, and I just twist it on. So it's not soldered or anything, so if I need to reuse the board, or change the board, if something gets damaged in the board, I could change it. It's easy to undo this. Sometimes I'll make connectors for these, but this one, there wasn't enough connections here to do that. So it also adding more connectors, there's some interferences when you put it in the box. I tried to keep it more slim to avoid that. So anyway, this was just an aid to me. I colored these in, so it makes it easier for me to connect the board. So this is a photo of the overall system, and I have the boards outside the box right now. You can see these screw holes, and there's standoffs here that I could actually screw these in and install them in the box. But what always happens, something always breaks, and I found it much easier. I got this styrofoam lid from medications that we get in the mail, and it makes a good insulator that you can put electronics on. So I save these tops and use them to put my electronics on if I want it very well insulated. And so I used one of those. And this is the power supply. So there's basically not too many components. There's the Nucleo board, there's the PCB board, there's the power supply, and then there's the box itself. So there's basically like 4, maybe you include this LCD, maybe 5 main components to the system. So this is a description of the system. So the electronics modules are shown out of the box. The modules can be placed inside the 1590D aluminum box, but for this learning experience, it is best to keep them out of the box for easier repair. This system is for research and educational purposes only and not intended for production model. The system is powered off a 5-volt DC USB power source. So the basic electronic modules is the Nucleo board that you can buy off the shelf from DigiKey. So there's a PCB board that contains the codec, and I'm going to provide all the Gerber plot files and the KiCad files, and I have all that. I'm going to provide that. This is the Gerber plot files, so I'm going to provide that. And I also have a bunch of reference documents, the main reference documents from Texas Instruments and STM Microelectronics. So we have this PCB board that has the codec on it, and you could buy these codecs. I believe I bought a lot of them off of eBay for less than $5. And the power module, I believe I bought these off Amazon. So I have this power module. One of them provides 3.2 volts. It's the same power module, but you could set it to provide 1.6 volts. Then I have an SB24XXSN-220W. That's a little bit pricey. Believe that was like $12. I believe these are you could buy like 10 for maybe $5. Maybe they're about $2 each. And the LCD, the 1620 LCD 2-line display, I believe you could get like maybe 5 of them for $10 on Amazon. So this power supply provides plus or minus 15 volts. It takes the 5 volts in and provides plus or minus 15 volts. Use that for the op amps. And I probably could have came up with a simpler one-sided power op amp system, but I like going with the dual power op amps. Tends to keep the noise down. So you can see these three power supplies over here that take the 5 volts in and they put out 1.6 volts, 3.2, and plus or minus 15. All used for this board here for the audio codec over there. So now I'm going to talk a little bit about the user controls on this. And so we have a true bypass stop switch. It's a 3-pole double throw switch. We have the 6 assignable 500K linear pots. And we have the ones up, ones down, 10s up, 10s down, and 4 assignable switches. So we talked about that a little bit already in this presentation. So this is an overall system block diagram that I made, and yeah, try to see if I could zoom back on that. So this is an overall block diagram of the system. So this is our aluminum box, and this is the Nucleo board. So we have the 5-volt USB power coming in, and that actually comes out, and it feeds this Nucleo board. It provides the power for the Nucleo board. It's just a straight 5-volt USB power, but it also comes out and feeds these 3 power supplies. So it feeds the plus or minus 15 volt power supply, the 1.6, 3.2 volt, and that's used to power the audio codec and the op amps. So there's a right guitar input and a right guitar output, and those are just go through the processor, but the left guitar input goes through the stomp switch, and it could either be when in true bypass it's just the output of the guitar, but when it's not, then it's the output of this processor. So there's 6 pots, and that interfaces with the Nucleo board, and there's 8 discretes, and that also interfaces with the Nucleo board. So it's these 8 switches, and the I2C interface from the Nucleo board feeds a 1620 display that controls this display. Now between the Nucleo board and the PCB board, I have the I2S interface. There's a transmit and receive on that. But the I2C interface also talks to this from the Nucleo board, which sets up the registers. So there's audio inputs. There's 2. The stereo audio inputs goes to this, and the audio outputs goes back out to the box, and that gets distributed to the right and left guitar output. So this is just an overall block diagram. So this represents the main processor, and then this represents the audio codec. So let's see what else we have here. Okay, so we're going to talk a little bit about the PCB board that was made. So a custom PCB was made using KiCad. The primary purpose of this board is to host the TLV 320 AIC 3254 audio codec. The schematic was first made using KiCad. So this is a schematic that I made, and so I had to maybe like a lot of unnecessary jumpers because this was a little experimental. So I wanted to be able to open up any pin as I developed this. So a lot of the circuitry comes right out of the data sheet for this chip here, the audio codec, and I have the data sheet here. We could take a look at that for a second. Under reference documents, this is the data sheet for that, so you can take a look a little bit. This is a block diagram of the audio codec, and if you go through this, it has some suggestions. Maybe not this document. There's also another reference document that has all the I2C registers, and it has some recommended designs for this. So yeah, maybe this might be shows like a typical application here. So some of the capacitors that I use have to do with this. There's also the other thing, under the reference documents is this application interface. So that's a bigger, maybe more important document that shows all the registers and great reading. It was a big learning curve to learn how to do this stuff. So just follow the data sheets. So anyway, this is the schematic I drew up in KiCad. And then KiCad is kind of magical. So I was able to make the board and actually use the auto router, so I didn't have to route all these little traces, which made it a lot easier. So anyway, here's another picture that shows the utilization of the pins on the STM32H723ZGT microcontroller. So anyway, why use an audio codec rather than the ADCs and DACs? Now there are ADC and DACs built into this processor. I had tried using them before, but the sound quality was pretty bad. So this STM32H7 does contain 16-bit ADCs and 12-bit DACs. However, the audio sound quality is not good on these type of ADCs and DACs. So the 32-bit audio codec was found to work better. However, the ADCs and STM32 are used to read the potentiometers. So I do use the ADCs here to read the potentiometers. So next I'm going to go into some very simple software coding to show you how maybe some of the software works in this. Some of the very simplest ones. So I'm going to shift gears a little bit and talk about the software. It's very simple ones. And I'm going to demonstrate them to you pretty soon. So the first very simple effect I'm going to do is, this is the simplest effect you could possibly do. This is a pass-through effect. It does nothing. It just passes the ADC to the DAC. So this is the simplest effect, which isn't really effect. It's just a pure feed through. So this one I called effect 9 on my system. So these are some of the parameters I needed to set up first over here. In fact, this is, I believe, yeah, that's all. This is the whole thing here. So I have a gain which is set to 1, and I have an input and an output. I initialize those as 0. So this is the code. So I take the left ADC input and I feed that to the input, and I make an output. And the output is just equal to the gain. It's 1 times the input. So it says here, yes. So we'll go through the comments here. So set the gain to 1, declare the input and output parameters, assign the left ADC to the effects input, set the effects output to the effects input. So that's just doing that. Then I assign the left digital and analog to the effects output, and I do the same thing to the right ones. So the left and right are the same. So this output now is just equal to the input. So the output's equal to the input. So we'll demonstrate that effect. It's just a straight, whatever goes in comes out. So but it's a good example just to show you that I could send audio data through this device. Okay, I'd like to demonstrate effect 9, which is just a pure feed through. So I have the system on effect 9, and I'm going to play a few things on the guitar. Just play through a couple notes. So you can hear the sound just feeds right through. So the next effect I'm going to demonstrate is a code listing for a simple digital delay. Okay, so now we're getting into some real effects here, and we're going to talk a little bit about circular buffers here, which is important if you do a digital audio digital processing system. So this is a code listing for a simple digital delay. Okay, and we're going to demonstrate this. This is effect 0 in my system. There are 2 circular delay buffers used for the audio signal with a 20,000 hertz update rate. the array size of 20,000 will provide 1 second maximum delay buffer for each channel. So we're kind of a little bit limited in RAM in this system. It's not as good. We could get maybe about 1 second per channel. This device isn't too good at storing data. At least I don't have doesn't have the RAM in the system. So anyway, we declare some arrays for the circular buffer for the left and right channels. So these are just arrays, floating point array, 32-bit arrays, but there's 20,000 reserved for the left and 20,000 reserved for the right. So this is an example of programming a digital delay using a circular buffer. So these are some of the left channel parameters. So I have my left input, my left output, and then I have a thing called a dry gain and a wet gain, and these are just some gains I made up. I just set them to 1 to keep them normal. So then I have some indexes. So I have a left channel index, and so I have one just called index left, and then I have a thing called delay left. So I set delay left to 19,999, which is 1 less than 20,000. And I do the same thing to the right channels, or right channel also. So I want to do both of them to demonstrate both channels are working. So this is initializing the parameters. So whenever I do one of these, it's very helpful to make a drawing of a circular buffer. So I did that here, and this represents each memory location. So it starts at 0, 1, 2, 3, maybe of the array. So in our case, this n goes up to 19,999. So there's 20,000 of these. So we can see the index always starts at 0 under like Fortran and other languages. So in C is kind of like an odd one. You can really start the index wherever you'd like to, but just sticking with the way C code is done. So I made this little drawing. So we'll look at this a little bit and the code at the same time. Maybe I could zoom out here a little bit. It might be a little hard to see, so we'll fit this. So anyway, the way this works is that I'm just going to utilize the maximum buffer. So if my buffer is 20,000 memory locations and I have a 20,000 hertz update rate, that's going to give me, at most I could get is a 1 second delay. So the first thing I do is I assign the left ADC to the input. So this is the input here. So basically I'm just reading the ADC, and that's what it's shown here in the circle. Say we're at index 0. So it's kind of arbitrary where our index is, but we're going to start at 0. So I read the ADC. So then in software, I'm going to make this output. So I have a dry gain and a wet gain. I just set those to 1. So I take my input. My current input is this, and I multiply that by 1. I take my current input and multiply that by 1. That's our dry input, our dry gain, which was set back here. That's over here 1, 1. So what I do is I take my output. It's equal to 1 times the input plus 1 times this, what's in the buffer. So that's over here. So I first read the data, then this arrow here, this arrow, get past data and mix, represents this line over here. So mix current ADC value with the past ADC value. So that's what I'm doing here. And then right after that, I store the data. I store it in here. And then I increment the index. And then I repeat. So what it is, when I got the data, it was the data that was stored 20,000 frames ago, which is 1 second ago. So this is the line that stores the data. So I take this, what I just read into the ADC, now I store it. So that's what I did here. So then I repeat, and I go all the way around. But I need to do a check here, because what's going to happen when I hit when I hit 19,999, I'm going to run out of memory. So what I have to do, so I increment, this is the increment step, that represents this over here. So I'm starting with my index at 0. But what's going to happen if I have to do a check here. So if my index, that's this index here, when it hits 20,000, what I do, see this is set to 19,999. We'll go back here and check that. That was this over here, this EOO delay L. So yeah, so the strategy I use in my software, I always begin the parameter with the effect, with the all the variables with the effect number. So that's how I kind of segregate the different effects into the same software. So anyway, so if this goes, when this hits 20,000, it's going to reset it back to 0, and then and then I set the output, that's this over here, to the DAC, to the digital analog converter. So assign left DAC to the left effects output signal. So then I do the exact same thing for the right side. So anyway, it helps to draw this circular buffer here. So what happens, it does this and repeat all the way until it hits N, which is 19,999 in our case, then it resets N back to 0. So anyway, that's an example of a digital delay, and we're going to listen to that pretty soon. So now I have the box on effect 0, which is the maximum circular buffer delay. So I'm going to play a couple notes to demonstrate that. So I'm going to go to the guitar now and play a few notes here. So you can hear the delay. So now I'd like to talk about a little bit different type of digital delay with a variable delay controlled by the pot. So this gets a little more complicated now, but it does help to draw a picture here of our 19,000 or 20,000 memory locations. So we'll talk about this one next. So this one, we use one of the pots to vary the delay around. And so this gives us a way of doing a variable delay. It's another circular buffer, but a little bit different than what we had before. So up here, these are some of the parameters. We want to have a quarter of a second delay here. Well, that's like our nominal delay, and we're going to do plus or minus 100% around that, which would be 0 to 0.5 seconds. So this is effect 13. So we have some indexes. There's an index 1 and an index 2, and this is our nominal setting for our delay width. And we have a dry gain and a wet gain. So we mix the original sound with the delayed sound. And there's an input and an output parameter. And this is another index here. And this is our maximum delay. Our maximum delay is we have the 19,999, which gives us the 20,000 memory locations. So we'll look at the code here a little bit, then we'll go back to this picture. So we'll see how this is set up. So this pot, the way it works, it varies from -1 to +1. And so what we do is the first thing is to read the ADC in and set that to our input. And we're going to figure out what our, like we're going to get a number here. That's the number would be an integer that would give us how much delay. So it says pot 1 ranges from -1 to 1, and this is an example where like a temp, there's a temp could vary from 0 to 10,000. So let's say a temp is 5,000. So that's our delay there. So 5,000 would be a quarter of a second because it's 1/4 of 20,000. So there's another little if statement here. We don't want a temp to be less than 2. Would be like our minimal delay. So what we do is we cast the floating to fixed point. So this index 1 is equal to 5,000. So this is going to be 5,000. So if we take our sampling rate, which would be 20,000 times 0.25, that gives us that would give us the 5,000 if our pot was set to 0. So there's a check here if the index is greater or equal to 5,000. So if it's greater or equal to 5,000, we use this to compute index 2. So index 2 would be beginning with 0. So we take index and subtract index 1. A little bit hard to understand, but we'll go back to the picture. So if the index isn't greater or equal to 5,000, we use this other little equation here. So there's a lot of different ways of doing this. This happens to be one way of doing it. So this is our mixer here. We mix our original signal with the delayed signal, and then we store it back into the buffer. So this is our array, that's a buffer. Then we increment index, and this index, once it hits 20,000, we want to reset it back to 0 again. Then we set the output to the digital analog converter. We do the same thing for the left and right side. There's really only one signal here. So basically that's the algorithm there. So we'll go look at the picture a little bit and try to discuss how this works. So in this case, we still have this incrementing index that stores the ADC, increments the index, stores the ADC, increments the index. But anyway, let's say we have this 1/4 of a second delay. So we're actually starting with this at 5,000. Now if we had less than 1/4 of a second, we would be in this region. If we had more than 1/4 of a second, we'd be in this region. But we don't go over the 1 second. The most we could have is a 1 second delay. So anyway, so what we do is we read the ADC over here, and we get the past data and mix it with the current data, and then we write to the DAC. So we write to the DAC, and then but at the same time, this other thing is happening where over a 1/4 of a second previously, the data was being stored and incremented. So it goes around, and so if if index is larger than index 1, we set index 2. See, it's actually index 2 here is what's being incremented and setting this. So you might have to go through this a little bit mentally. So we get the past data at index 2. So the data in each frame is being stored at each memory location, and this is incrementing. And then when it is greater, if index is ever greater than 20,000, it resets to 0. But in the meantime, what's happening? It's this index 2 that we're using to look at the past data. So when we do this mixing, so if index is larger than index 1, now index 1 is kind of fixed. Like the pot varies around, but say it's fixed. Say it's set to 5,000 in this case. For the 1/4 second delay, it would be 5,000. So if index is larger than index 1, set index 2 to index minus index 1. So index 2 is set to say at this point index is equal to something greater than 5,000. So index is 5,000. So if we're up in this region here, we set index 2 to index minus. So let's say we're at 5,001. So then so then we would be 1. So we would be reading this as the pass value, 5,000 back. Now if index is less than 5,000, then we set index to the delay, which is 5,000 plus 1 plus the index minus index 1. So that's 5,000 also. So let's say we're at 5,000. So this would cancel with that, and then it would just be so if we're in this region here, let's say we're at 5,001. I mean, let's say we're in this region. We're less than 5,000. So it's just going to go back that amount. Anyway, you'll have to like mentally look at it yourself to see how this works. Sometimes it's good to simulate these algorithms. There's other ways of doing this. This isn't just the only way to do a variable delay, but this works. So this is another algorithm that we're going to hear soon. Okay, this is effect 13, which is a variable delay, and I have it tied to pot 1 over here where I can vary the delay. So let's go to the guitar. I'll play a few notes and I'll vary the delay. This is at a middle setting. Pretty short delay. So now I'll go back to the pot here, and I'm going to turn it up a little bit to get a longer delay. So we'll go back to the guitar now. Pretty long delay. So now we'll go back to the pot now, and we'll turn it all the way down, try to get a short delay, see what that sounds like. Can't hear much of a delay there, so I'll turn the pot up a little bit. You can hear it's a pretty fast delay. I'll try to play something a little more on the guitar. Anyway, I'd like to show you at the very end of this little write-up, I have some important references. So we have the data sheet for the audio codec, and there's this application reference guide that has the I2C registers for the audio codec. So these are the most important documents to have. You want to have a good set of your reference documents. And this is a little brochure on the Nucleo boards. And over here, this is a user's manual for that Nucleo board. It's an MB1364 board. And this one isn't as important. It's getting started with software development. Now we're just using Cube IDE, but there's other software development tools such as IAR or Keel, and so this talks about that. But if you're just using Cube IDE, this isn't that important. So this is the data sheet for the processor, this document here. And then we have a reference manual. It's very big. This is like 3,000 pages. If you want to know more about the processor. And this is a programming manual for the processor. It goes into the machine language instructions, although we don't have to worry about that. We're doing everything in C. And this is important. This is the drivers. They're called the HAL drivers for Cube H7. So the coding files, there's really only 2 files that I need to put code in. Everything else, all the other files, only 2 files contain the code that I enter for this project. All other code files are generated automatically by Cube IDE. So this one is the one that sets the interrupt. I only really put 2 lines of code. So I'm going to go through that in the coding presentation for this. And then main C, that's where that contains all my code. So every effect is in here, all the parameters, everything that's needed. So there's really only 2 files that I have to edit. So anyway, this is part 2 of the series, and I'm going to get more into it, and hope you find this interesting.